Hi. So today I'm going to show a piece of equipment I got from a friend. This is the HP115BR frequency divider and digital clock. It requires some external instruments or clock generators to basically drive it. In the original setup, I have both of these equipment actually with me, but I'm not going to be using them to drive this clock. It requires a GPS receiver, the HP11503A or some equivalent, which creates a 10 MHz output clock, which goes to a timing generator which provides a 10 microsecond pulse train, which is at 100 kilohertz, which is what this instrument requires. And this is HP15308A. So the actual block diagram is shown below over here. We have the 100 kilohertz clock coming in, and it goes through two regenerative dividers. The first divides by 10 to get 10 kilohertz, and then further divided by 10 to get 1 kilohertz. Inside the regenerative divider, this is completely analog, by the way, there's no digital gates or anything. It's just using mixer and some tuned amplifiers to create an IF frequency, which is actually the 10 divided by 10 clock, and it's all sinusoidal waveforms actually. So coming out of this 1 kilohertz goes into a resolver, which actually allows you to tune the phase of the output with respect to the 1 kilohertz. So you can shift this output phase over here by plus minus 1 millisecond, which is the 1 kilohertz period, and it's got a resolution of 1 microsecond. It's quite an amazing piece of equipment and actually works. That output then goes into a driver amplifier, which drives a synchronous motor at 1 kilohertz, which then is geared down to provide to drive the digital display, which is also a set of drums with rotating digits. It's quite amazing. That in itself is something to look at. It's quite noisy when it runs, but when it's inside the case, it can be somewhat subdued, but it's still, you can't just have a conversation with this thing running all the time. It's in that sense it is a bit noisy. And using some photocell and a bulb, there's a light signal that goes through this disc, which then is used to create some kind of a pulse, 1 kilohertz pulse, which is gated by this one to create this 1 hertz kind of a tick-tock kind of signal, and going through two blocking oscillators and then a transformer and a multi-vibrator to create the 1 hertz output. This 1 hertz output is available on a BNC jack, and so are some of these intermediate signals, the 10 kilohertz and the 1 kilohertz. So this is quite a versatile instrument. I believe this was used in the 60s along with the cesium clock coming in to create a unit which was self-contained, and it was carried in aircraft apparently and tested and so on, and extremely accurate, of course, based on the fact that the cesium had an accuracy, I think, of 2 times 10 to the minus 11 seconds, or 20 picosecond accuracy. So that, if you translate it to seconds per years, it's like a 1 second error in 1,500 odd years. So based on this reference accuracy, one can use this as a very accurate clock. One of the interesting blocks in this HP divider is really the regenerative divider. The rest of the blocks seem to be generally normal standard electronics, amplifiers and mechanical components and so on, but to me this was interesting. I've never seen anything work like this before, at least in my experience, but I thought I would try to understand or explain what's going on here, and others who are more knowledgeable than me can explain if I didn't said something wrong. Anyway, this is the 100 kilohertz clock coming in from the outside for the first regenerative divider. It probably goes through an amplifier section, which then is there's some filtering going on right there. The 100 kilohertz then enters a mixer, which is then mixed with a 90 kilohertz coming in, and that output is a 10 kilohertz. When you mix this, you get the sum and the difference frequencies out of the mixer plus other harmonics. But let's assume that we somehow can filter out the 10 kilohertz out of this thing, and this basically amplifies back, creates a multiply by 9 through this loop and comes back as 90 kilohertz. To me, the interesting part is how do you get to 10 kilohertz when there is no 90 kilohertz to start with. There's only a 100 kilohertz clock, and everything else here is just derived off of this 10 kilohertz, which seems to be coming out of nowhere. To my understanding, these are tuned circuits. So this one is probably tuned at exactly 10 kilohertz, and then this one is tuned at 30 kilohertz, and then this is tuned at 90 kilohertz. And based on the fact that when there's some mixing going on here, there's noise components at, let's say, at the beginning before the whole thing starts up. There'll be noise components which are broadband in some way, and then there are, of course, these other components which would be existing when this thing locks. That is, these components over here, 10 kilohertz, 100 kilohertz, 190, 290, and so on. And once you lock onto this 10 kilohertz through this loop, to this band pass filter, then you amplify it, you create more harmonics here, and the harmonics are the 10, 30, and the 50. You select the 30 kilohertz harmonic and go into the amplifier again, and again you get 3 harmonics and beyond. You select the 90 kilohertz, and that comes back, and this loop self regenerates, and that's how this thing works. Of course, to make it in the beginning, when you power on this thing, this does not actually self-start, and I think this amplifier just goes into the output maybe 0, and is just out of there's no, it's one maybe a stable situation. Now when you hit the start button, it shorts this node to this node, that is the 30 kilohertz output of this filter, into the 90 kilohertz into the mixer, and that creates some jolt in this circuit, which creates probably some energy which kicks this thing out of its stable state. And then because of the fact there is some energy in this in the system, it eventually finds that 10 kilohertz and locks to it. And once you get 10 kilohertz, this will not move. Any other frequency that comes out of this mixer actually will attenuate itself to 0, or the frequency will blow up to the point where the amplifier cannot sustain this loop. So the only way this works is if this is exactly 10 kilohertz, and you can actually verify that by going through the loop multiple times. If you just offset this by even by microhertz, this thing will just diverge at some point. And then once this 10 kilohertz is generated, this is probably a small signal over here, then that gets amplified and goes to second regenerative divider, which is running at 1/10 of this frequency, same principle, 9 kilohertz coming out into the second mixer, and eventually you get the 1 kilohertz output. So here's the front of the unit itself. It's now not running, obviously. If it were running, it would be very noisy in here. There are a bunch of things I want to point out over here. One is this interesting debugging or method to actually check if all the circuits are working. So we have multiple selections over here. One is the supply voltage, which is right now turned on, which you can see is sitting at a level of 7. And actually, if all these dividers are working properly and the currents are right, then all these circuit check will be somewhere in the 7 kind of value. So it's some kind of an analog way of displaying circuit functionality. So right now, if I switch to the 100 kilohertz, you'll see it's gone to 2, which indicates it's actually 0. I'm sorry, and then all of these are off, so there's nothing coming out. There's some current in the clock, but most of these will be reading 0, except for the supplier when it's on but not working. So I'll show that later when it's working. Then you have these different outputs: the 100 kilohertz output, the 10 kilohertz, 1 kilohertz, and the tick, which is the single 1 hertz output. And here are the hours, minutes, and seconds, and the hundredths of a second over here. And this will be rotating pretty quickly, and you have this sliding thing which shows a tenth of a second, I believe. And then you have the resolver over here, which has in milliseconds. This is now reading 47.710 milliseconds, or 47.710 microseconds, and then you can adjust that down to the 1 microsecond type resolution for the phase. That is, you can delay this 1 hertz clock by that much amount using the 1 kilohertz signal. So that's a 1 millisecond times 1000, which gives you 1 second over here. And of course you can lock this this vernier over here for the phase, and then this is the opening and closing. So once you slide that back into the unit, it locks it in nicely, and this is can be mounted in a rack. So that's the instrument. So here's the top portion of the instrument of the HP115BR. The front section over here is the mechanical, mostly the mechanical section, which I have to display, and on the back is all the circuitry. There are two sets of circuit boards, or actually they are just simple component mounting areas where each of these different transistors, resistors, capacitors, inductors are mounted, and they are connected just through wires which are then bridging these different components which are connected between two of these posts. So there's no actual circuit board or anything, it's just a very simple arrangement here. I guess for low frequency this works, and there's a lot of wiring of course that goes down into this thing and feeds different parts of the board of this instrument. And a lot of the big transformers are below this thing, and they are the ones that are used for the tuned circuitry for the active regenerative divider. There are two such dividers. One divides from 100 kilohertz down to 10 kilohertz, and that portion is over here, and there's another one which divides from 100 kilohertz to 10 kilohertz, and that's over here. There's also some all these germanium transistors are shown over here, are basically got some, I believe they're heat sinks, I'm not sure, but they're all mounted very nicely and screwed into the board, so they don't move around, and they are very securely connected into the board. There are a couple of transformers. You see these are small transformers, but the main transformers are as I mentioned, behind this, underneath this thing. The wiring that goes to the power and some of the inputs are actually at the back of the unit over there, and this is actually the plate that goes on top, and this is needed in case when you want to set the time, you need to have access to this part of the dials and so on. So the motor part is really here, which drives this whole gearing mechanism into this dials which show the time. There's also the resolver, which is used to fine-tune the phase of the clock, and that is got a very fine microsecond type resolution. So let's start this HP divider. So right now I have a 100 kilohertz clock from my GPS derived frequency generator going into the back of this. There's a connector for that, for the 100 kilohertz input, and it has to be large enough that it can work with that kind of amplitude, so this divider circuits can start up. So the first thing is to start the 100 kilohertz to 10 kilohertz divider. So I do that with using this one, and you heard that sound. Now next I'm going to start the 10 kilohertz divider, and I can hear that hum, which is the 1 kilohertz hum, which you can hear in the background. And now it's actually ready to start up. So there's also an annunciator which I'll show in the front panel, which shows different clocks running. So the only thing left is to now start the motor, and that is to use this particular knob. You need to twirl it to clockwise. Okay, started now. You can see the dials moving here, and this is moving at a 1 second rate, and this is the 10 seconds, minutes, and 10 minutes, and then the hours. So that's it. Once the clock runs, everything will start up and run. If there's any interruption of the clock, this whole thing will shut down. Let's look at the front of the unit. And here's the different selections for observing the supply voltage. So all of them must read around 7 in order to be valid. So the 100 kilohertz is reading 7, the 10 kilohertz is reading 7, the 1 kilohertz is reading 7. If any of these are not working, this will read either 2 or some other value, which means that circuit is inoperative. There is also a clock current, which is also okay. So here's the actual time being displayed. and the last is actually moves very quickly, you can't even see it. If I stop the clock, it will of course freeze at some location like a tenth of a second or hundredth of a second, which is the resolution over here, and then this adjusts the phase of that particular clock. If you want to precisely adjust it to the microsecond, which is, this is milliseconds, 58 milliseconds, and these are microseconds here, so you can move that in fine with a very fine pitch, in case you want to align it to some value. So right now I'm moving in 40 microseconds, 50 microseconds, and then there's even finer scales on the right side over here. So this is pretty amazing the way it runs. All you need is this very precise 100 kilohertz clock. Okay, so this brings us to the end of this video. So we looked at an interesting instrument which is completely analog but showing digital information, clock time information basically. This video described some basic functionality of the unit, showed the inside view. We looked at the startup of the digital clock, and also looked at the regenerative divider in some detail. I thought that was the real jewel in this design, how they managed to do that. The time accuracy of course depends on the external clock source. In the old days you use cesium clocks or other kind of receivers with fixed high accuracy clocks coming in, but today you can do it very easily using GPS derived oscillators and so on. It has the ability to set the microsecond precision on the final 100 hertz output, which also is pretty interesting. It has very low power consumption. We didn't look at that. It only consumes about 2 watt as I measured it, and runs off a 24 volt DC supply. It's of course outdated for today's technology with GPS time everywhere off the internet or many other sources, but it still makes a very nice mantelpiece, assuming it can handle this hum, 1 kilohertz hum that comes out, and some of the noise from the motor itself. So hopefully you enjoyed this video. See you next time. Bye.